Reluctance torque. We named its opposite number, mutual torque, in the last episode. This time, the other half of the story. Reluctance torque is produced whenever self-inductance, or self-reluctance, changes with position. Notice what's missing from that sentence. No second magnetic field. No mutual coupling required at all. A single coil, or a single magnet, acting completely alone against a piece of iron, can still produce torque, simply because the system wants to move toward the position of least reluctance. This is the mechanism behind cogging torque, which we covered all the way back in episode 1. But it's also, as you'll see today, the mechanism an entire class of motors is deliberately built around. Here's the single fastest way to tell reluctance torque and mutual torque apart, and it's a genuinely useful engineering test. Reluctance torque depends on current squared. An electromagnet attracts a piece of steel no matter which direction current flows through the coil. Reverse the current and it still pulls the steel in exactly the same direction. Mutual or alignment. Torque behaves completely differently. Reverse the current there, and the torque itself reverses direction because it depends on current to the first power, not squared. So, here's your test. Ask yourself, if I reverse the current, does the torque flip? Yes means mutual torque. No means reluctance torque. That one question resolves almost any confusion about which mechanism you're looking at. Reluctance torque itself comes in two flavors, and they're worth telling apart. The first, a coil's own self-inductance varies as the rotor turns. This is the mechanism switched reluctance motors are built entirely around. Salient rotor poles get pulled toward energized stator teeth. Full stop, that's the whole motor. The second flavor, a magnet's own flux travels through a varying reluctance as the rotor turns, even with zero current anywhere in the windings. That second flavor is cogging torque, the very first topic in this series. Same underlying equation family, two completely different physical sources, and as we're about to see, two very different reputations. So is reluctance torque good or bad? It depends entirely on what the motor was designed to do with it. Take switched reluctance motors. There are no magnets anywhere in the rotor, and essentially no mutual coupling to speak of. The entire machine is designed around reluctance torque, not around suppressing it. That gets you a simple, magnet-free, genuinely rugged motor, at the cost of higher torque ripple and more acoustic noise than a comparable mutual torque design. Now take a stepper motor's detent torque, the force that holds its rotor in place with zero current applied. That's the exact same physical effect that shows up as unwanted cogging in a BLDC motor. One mechanism, two completely different verdicts. Parasitic in one motor family and absolutely load-bearing in another. Let's close with the practical version of everything we've covered. First, the quick identification test. Reverse the current in your head. Torque flips, it's mutual. Torque doesn't flip, it's reluctance, because it only depends on current squared, or flux squared. Second, remember that context decides the verdict, not the physics itself. In a BLDC, or PMSM, reluctance torque is usually the parasitic ripple you're actively trying to minimize. In a switched reluctance motor, or a stepper's detent, it's the entire point of the design. And finally, here's the complete picture across these two episodes. Episode 7 covered mutual torque, magnets and currents working together. The useful torque in a BLDC, or PMSM. Episode 8 covered reluctance torque, self-inductance or self-reluctance acting alone. Between these two mechanisms, you now have every Newton meter that any electric machine of any kind is capable of producing.